All right, so we are talking chapter 17, I think, here, they say. So last time we talked about redox reactions. We went through, again, just to make sure everybody was on the same page, how to balance redox reactions in both acidic and basic condition. And again, you do have to do some of that, obviously, in part 2 of the lab that we did today. Basic first, there you go. And again, remember, those are the ones where we do have to add water to balance the oxygen. And again, for every water that we add to one side, we do need to also make sure that we take care of adding some H to the other side, 2 of them, to make sure that we aren't short in terms of hydrogen in this case. Then we started getting into really this chapter per se, which is about galvanic cells. And really, a galvanic cell really has kind of 2 parts or components, if you will. It has an anode compartment and it has a cathode compartment. And in the anode compartment, that is where oxidation occurs. In the cathode compartment, that is where reduction occurs. And when we do this, we typically fill both of these compartments with some solution. And in the solution, there is sort of the aqueous version of the solid electrode. So for example, if this was copper, in the solution here would be some copper 2 floating around, most likely. We have a wire that connects it, usually runs itself through a voltage sort of meter there, and it comes back down to the other side where we do have our cathode, which once again, if this was, say, zinc, we would have a solution of zinc basically floating around in here. We also have a really important component, as we talked about last time, which sort of connects both of the compartments, and that is our salt bridge. And as we talked about, really, sort of the function of the salt bridge is it is filled with an ionic compound, which basically will prevent sort of the buildup of the incorrect charges on both sides of the cell. So as we talked about, if you sort of take out the salt bridge on the left-hand side, because those guys are losing electrons and basically going from the solid into the liquid and becoming positively charged, you would definitely get a buildup of positive charge on the left-hand side. The same thing happens here. There actually is the electrons obviously transferring this way. As those electrons come in, it reduces the zinc, which basically takes it out of solution. And the result of that is you really have a buildup of sort of negative charge that would occur on the right-hand side there, because in addition to obviously the zinc in there, there's probably something like nitrate floating around in there as well with it that has a negative charge. And if we let that go, these negatively charged electrons would be actually then more attracted to stay here and would not want to go towards that negative side. So what the salt bridge does is it sort of filters in the negatively charged ions from the salt bridge into this side, positive charged guys to this side. And what that does is, again, keep sort of the right balance in terms of overall charge on each side of the cell, as there should be a slightly cell difference, potential difference between the cathode side and the anode side to sort of draw those electrons to the cathode side. Any questions on the parts there of the cell? We also saw that in an equation, say, like this guy here. So redox thing happening. We could also write this as like a cell diagram where we go with our anode first, separated by the salt bridge, which is represented by kind of 2 lines, to our cathode side, which is this copper here and that solid copper there. So this is what is sometimes referred to as a cell diagram, sort of a shorthand of how the reaction is happening. And it's always sort of written as anode first to the cathode here. And again, as we also talked about, you can pretty much dissect this into the equation by, usually always goes reactant product and reactant product over there. And again, that gets everybody on sort of the correct side of the equation. Other things that we also will see in here as well are things like pressure sometimes. We'll also see concentrations kind of put in there as well. Again, some electrodes are gases, like the standard hydrogen electrode that we talked about, which is basically the one that was assigned a voltage of 0 and what they use as a standard basically to compare everybody else to come up with what we talked about, which was the SRP values, which stands for standard reduction potential. And that is basically a big table of voltages that go with a bunch of reduction reactions. And that led us to an equation that we could use to solve for the cell voltage, which is basically the cathode minus the anode. And as we talked about a little bit last time as well, again, if you choose to use this equation here, we want to make sure that you do not change the sign that you find in the table. That is why it is subtraction there to take care of changing the sign for you. That's because the anode one is an oxidation reaction. And when you go to that table, everyone is written as a reduction, which means technically speaking, you need to reverse one of the reactions in there. As we did it with a couple of examples, if you choose to reverse the reaction and also the sign of the value that you find in that table, which is technically the correct thing to do because the E value should be correct for how the reaction is written. You would want to add those together. But if you're just simply trying to find a cell voltage, you can simply subtract the two values as long as you properly identify which one's your cathode and anode. And with that being said, our identification of the cathode and anode can be found by, if you are not given any information about the reaction, you're not given the overall reaction or anything like that, you can look at the SRP values, and the one that is more positive should be your cathode. And by default, obviously, the other one should be your anode in that particular case. With that being said, if you are given in words how the reaction is happening, or you're given an overall reaction, you do need to look at the actual equation and see what is being oxidized and what is being reduced to figure out what is your anode and cathode, as it may not agree with the more positive value. Any questions on any of that stuff there that we talked about? So talking about cell potential or the voltage, again, these electrons can go out and really do some type of work, and we can associate our sort of cell potential with our good friend delta G that we talked about in the previous chapter there. And the 1 joule of work produced or required by 1 coulomb of charge between 2 points is basically a volt. And basically the take-home message is the maximum amount of work that we could do is equal to Gibbs free energy. So there is sort of a relationship that we could apply the cell voltage to and basically Gibbs free energy to help us understand whether or not a reaction may be spontaneous or non-spontaneous based on what we get. And that equation that kind of ties those two together is this one right here, which is the delta G is equal to minus NF of E. Throw all these guys up here. There we go. So this equation here is a good one. That is our delta G is equal to minus NF of E. N is the number of moles of electrons. It is the total number of moles that have been transferred. So what I mean by that is if you have 2 half reactions, you're looking at it on one side, it says plus 2 electrons. And on the other one for the reduction, however, it says 2 electrons plus. N would be, in this case, 2, not 4. So you don't want to add those together. So it's just 2 electrons being lost by the guy that's being oxidized, same 2 electrons being gained by the guy being reduced. So in this case, N would equal 2. So sometimes people want to add those together to get to N or something like that. Faraday's constant is a constant. You can use this number, which is 96,500. Sometimes it's 96,484-ish, sometimes used, but we will reduce rounded number here. E of the cell here is our cathode minus our anode. So this is, you go for your SRP table and do your cathode minus your anode. And obviously that would give you your delta G value. So when we look at this equation, delta G is negative in a spontaneous process, right? And the only way to do that here is to have what type of charge of voltage, positive or negative. We would want a positive cell voltage, right? Positive, and that negative will give us a negative overall for delta G, as the mole should be a positive number and F is a positive number. So when you do get a positive cell voltage, that will result in you getting a negative delta G, and it will be a spontaneous reaction, which is why positive voltage is good. If you end up with a negative value for E, that negative and this negative here will then turn your delta G into a positive, which means we would get our non-spontaneous process occurring. So that's why we typically don't want negative voltage when we make a galvanic cell, because it's sort of a non-spontaneous process happening. The good news is you can just switch the anode and the cathode and it would turn into a positive value. But positive voltage results in a spontaneous process and a negative delta G. We could also relate our cell voltage to the equilibrium constant, because what would this class be without K here? There we go. And this is the equation that we get to for our equilibrium constant. So this once again is our cathode minus our anode. And all the rest of them are all still the same guys. Obviously, R here is the 8.314 version. And T is our temperature in Kelvin. N is our moles of electrons. F is our Faraday's constant. And K is our equilibrium constant, like normal. Now, sometimes people will use these couple of equations on the bottom, because at 25 degrees, 3 of those things become like a constant. All of those 3 things that they canceled out here, these 3 guys. And it can reduce down to E of the cells 0.0257 volts divided by N natural log K. Or if you like the base log 10 there of log, you can do the 0.0592 divided by N log of K. Personally, I roll with the top equation here and just plug in all the numbers, even at 25 degrees. It just seems easier. And again, so if you don't want to worry about these 2, they're really just a version of the top one. This is our trifecta of death here of between E of the cell, delta G, and K of our thermodynamic properties. Obviously, this is the way you could get from one to the other by using these equations, including one obviously that we saw in the previous chapter there. Our delta G is equal to minus RT, natural log of K. So if you're given some SRP values, and you want to know, is the reaction spontaneous, calculate delta G, the top one would probably be the one you want to go with. Obviously, anything involving an equilibrium constant, either you need to calculate it or you're given an equilibrium constant, then obviously the bottom equation there would be the one that you would want to look for and use. Any questions on that there? All right, so as I mentioned before, the relationship that we see here, positive E will result in a negative delta G, and that does favor product formation of the reaction going from reactants to products. Opposite is true. Negative means that we would favor reactants in that case. And if you had a no voltage, you'd be sort of equally favored in either direction. No voltage would basically zero out our thing to a 0 delta G sort of guy. All right, so why don't you give this one a try? Calculate the delta G naught for the following reaction, and is it spontaneous? Let's see what you come up with here. These again are the SRP values you would find in a table. Okay, let's take a look. So obviously we're looking for delta G. We've got some SRP values. So our equation we just saw there, minus NF of E there. And we would want to use that equation there. And we would want to calculate, obviously, our E of the cell. In this particular case, the one that's our cathode is the copper, and it is the copper because of looking at the equations going from +2 to 0, which means it is being reduced. This guy's going from 0 to +2, which means it is being oxidized. So we want to make sure we do look at the equation here, and it does happen to agree with the one that's more positive in this particular case. That means our E of our cell here would be our cathode, which would be 0.34 volts minus, and again, I'm going to subtract since I'm not going to change the sign, so that will do it for me there. And that's going to get us like a 0.34 and a 0.44 and a 0.78 volts. At this point, we can then go into our delta G, which would be minus, and we can see from the equation here, it is 2 for N. So N would equal 2 moles. Our F would be 96,500 joules per volt per mole. And then I ran out of room, so we'll multiply that by 0.78 volts there. And that would get us about negative 150,540. By the way, the units here would be joules at this point, which gets us approximately minus 151 kilojoules if we kind of convert it over. Any question on any part of that calculation? This reaction, would it be spontaneous? The answer is yes, it would be. And basically, as soon as we got this number right here and saw we had a positive voltage, we could pretty much make that decision at that point because of the E being positive. Any questions on any of that? And obviously, we got a negative delta G. So it didn't really specify in this case, so you technically could give it an either one. But normally speaking, like we talked about, delta G and delta H are normally given in kilojoules, and delta S is the one that's normally given in joules. But again, if it really doesn't specify, you can go either way on it. Other questions? All right, so let's try another one here. Will 1 molar nitric acid dissolve gold metal to form 1 molar gold 3 here? So first off, our cathode is which one? Cathode is which one? The cathode is this guy? No. I'm gonna go with the top guy. The reason is, if we read what it says that will nitric acid, which means it's a reactant, dissolve gold metal, which would be gold with no charge, to form gold 3. So this is really the reaction we're looking at, which means my gold 3 actually needs to be on that side, and that would then make it an oxidation reaction, which means the unhappy face here is an anode, and this guy actually would be our cathode. So again, it's really important if they sort of give you the information or give you an overall reaction that you do look at it and see what's going on. So with that being said, we will then calculate our E of our cell here, which would be E of our cathode minus E of our anode. And in this case, our cathode is the 0.96 volts minus our anode, which would be 1.5 volts. And in this particular case, then that would basically give you a negative 0.54 volts, which really at this point, we can make the determination, will this happen? The answer is no, it will not happen because we have a negative E, right? Which means if we put it into our delta G is equal to minus NFE, with this guy being negative and that negative there, that is going to definitely turn us into a positive value for G, which would also mean that it is non-spontaneous as well. We obviously could calculate the value of G if we wanted to, but since it didn't ask, we won't do that. N would be 396,500, obviously, for a Faraday's constant. Question on that there. This is why when you used to bring your gold into like a pawn shop, they would take some nitric acid and they would put it on the gold. If your gold's still there, it's gold. If gold's not there, should have went to a different pawn shop maybe, I don't know. But, you know, it would obviously turn colors and sort of despair. So you could learn things by watching TV, right? They don't have those pawn shows on anymore like they used to, but years ago I used to watch those shows and they show that. Any questions on any of that stuff there? All right. All right, so let's try this one here. Let's do something. What is the equilibrium constant for the following reaction? I think you have the SRP values on your handout. Yeah, I think with that. Okay, so why don't you give that a go and see what you come up with. What is it? The iron is the SRP value for iron? Negative 0.44. Yeah. And the silver? 0.8, positive, right? Okay, perfect. you don't have it. Okay, let's take a look here. So first off, our cathode is the iron in this case, and the anode is the silver. And we know that by actually looking at the equation that they gave us. So it is the iron when we look at the actual equation going from +2 to 0, which means it is being reduced. And when we look at the silver, our silver here is going from 0 to +1, which means it is being oxidized. So once again, here it does not agree with the SRP sort of table, but we do want to look at the overall reaction. That gives us those two reactions as well. In addition, when we write out our reactions here, if we balance everything out here, we do end up with obviously an N value of 2 in this particular case. We're going to be looking for our K, which means the one that we saw would be our RTNF, natural log of K. And in this case, we're solving for K. So we do need to calculate E of the cell. So we could do that by taking, once again, our cathode, which is the iron, minus 0.44, minus our 0.8, which is our anode, getting us a 1 point something there, 1.24, that is negative voltage here. Everything else on the right-hand side is pretty much done except for natural log K. So that would get us a minus 1.24 volts is equal to 8.314 joule per Kelvin per mole. Our temperature converted into Kelvin, so that's a 273, gets us to a 298. Our moles that we saw from the balance equation, which is 2, and our 96,500 joules per volt per mole is equal to the natural log of K. Going to just kind of clean up everything on the right-hand side before the natural log there. So that will get us 8.314 times 298 divided by 2 and divided by 96,500. Gets us a minus 1.24 volts equals 0.012837716. I don't feel like rounding. We will take this and divide it to the other side there. 1.24 divided by our answer gets us a negative 96.59. I do a little rounding now. Natural log of K at this point. We are going to take the E of both sides. And there, obviously when we do that, we get the K. And if we take this and take the E of it, looks like 1.1 times 10 to the minus 42. Any questions on any of that calculation there? Do these two numbers agree with each other? The answer is yes, they do agree with each other because that is a negative E, which means this reaction is spontaneous or non-spontaneous. Non-spontaneous, which means it should be hanging out on the reactant side, right? And if it's hanging out on the reactant side, that means that we should have a large or small value K. We should have a small value K, and that definitely is a small value K. So all those things do kind of make sense. Clearly, if you had a positive voltage and got that K, that should not make sense, right? Because that should be the opposite effect. Any questions on any of those there? So let's talk a little bit then about the effect of the concentration on your cell voltage. And this is what is sometimes referred to as the Nernst equation. And that's this guy right there in the middle. If I roll it around, there we go. And Nernst equation really is sort of built off of all these other equations we sort of saw previous to this. And much like the delta G equation that we saw in the last chapter, where this is, again, you could kind of think of it as delta G under some non-standard conditions. Remember, standard conditions means if you're dealing with gases, all the pressures has to be 1 atmosphere. If you're dealing with concentrations, they all has to be 1 molar. And obviously temperature should be 25 degrees Celsius. So if any of those things are not those values, That will get you sort of that non-standard condition. And that's pretty much what this is as well. This is our basically cell voltage under some non-standard condition. Again, very commonly pressures are different than 1 or concentrations are different than 1. Everybody else in this equation is pretty much the same stuff we've been using. This once again would be from our table of cathode minus anode. Obviously RR, here's our 8.314 that we use. That's our temperature in Kelvin, our moles of electrons, and obviously our Faraday's constant, same guy all the way around here. Q is the reaction quotient, which we've used many times over the semester, which once again is the products divided by the reactants. It is calculated the exact same way as we calculate K. So once again, we want to make sure we use our coefficients as the exponents when we do that. Just like we saw in the previous equation, you could reduce it down to these guys if you're at 25 degrees. But once again, personally, I just stick it into that equation, even if it is at 25 degrees, and kind of put the numbers in. I will say, you know, this equation, the one we saw previously, you know, if you do choose maybe one of the bottom equations on each of those pages, depending on how you round, you may get a slightly different number. But usually the exponent part should be the same, but the front part of the number may be slightly different. By the way, this equation is how we get to the previous equation we just used, because when we hit equilibrium, E is equal to 0 and Q would equal K, which means basically this guy becomes the equation we just used, which was the RTNF natural log of K. So that's basically how you derive the previous equation that we just used from the Nernst equation to get you that. Any questions on that there? All right. Then why don't you give this a go and see what you come up with here. And once again, you should have your SRP values going on here, I think. And they are, one more time, is iron was still the minus 0.44 volts, I think, right? And the cadmium, negative 34, thank you. 0.4, thank you. That would probably be better than that one. 0.4. So negative 0.4, right? Okay, perfect. Let's take a look here. So in this particular case, this is under sort of non-standard conditions, and I know that because I'm given some concentrations, and those guys are not 1 molar. So that tells me that I should probably be using the Nernst equation here, which is really what that's for. And that again would be my E, which would be sort of my non-standard voltage, is equal to my E naught minus RTNF natural log of Q in this case. So in this case, our cathode would be which one? The cathode, once again, is the iron, looking at the actual equation, +2 to 0 becoming reduced, while the cadmium goes from 0 to +2, which is being oxidized. So to calculate my E of the cell here, taking our cathode, which would be, again, the iron, minus 0.44 volts, minus a minus 0.4 volts, gets us a 0.04 volts. That is negative in this case, I believe. So under standard conditions here, is this reaction spontaneous? It is not, right? We got a negative voltage. So we're not under standard conditions. We kind of play with the concentration. So let's see if that makes any difference. Our R is obviously a constant. Our temperature does need to be obviously converted into Kelvin, which would give us 298. Our N in this case is 2, right? +2 and +2, so that's 2 electrons. Obviously Faraday's there as a constant. So our Q would be our products, which would be the cadmium in this case, divided by our reactant, which would be the iron. And once again, obviously we would not include anything that's solid, just like we wouldn't with K. That means when we put this in here, it's going to give us a 0.01 divided by 0.6. And that gives us a Q value of 0.01667. At this point, we got everything we need, really. So we'll just put it in. So our E of the cell was a whopping minus 0.04 volts, minus our 8.314, which is obviously our gas constant, our temperature, which we converted to Kelvin, divided by our 2 moles and our 96,500. And that would then equal the natural log of 0.01667. Once again, I'm going to do a little cleaning up of the left-hand side here, and then I'm going to multiply it by the natural log of 0.01667. Actually, I'm just going to do that. Yeah, so we'll do the right-hand side cleanup. So I'm going to take the natural log of 0.01667, hit equals, going to multiply it by 8.314, multiply it by 298, come back and divide by 2, and divide by 96,500. Gets us a minus 0.04 volts minus a minus 0.0526 volts. Now adding these together, minus 0.04 minus a negative 0.0526 gets us a whopping 0.013 volts happening in this case. Is this reaction spontaneous? It is, barely. It's got some positive voltage. So this demonstrates the idea that, you could potentially have a cell that would be a non-spontaneous reaction and under standard conditions, but you can play with the concentrations. You can play with pressures if you've got gases going on there, and even the temperature, and you can maybe turn it into a spontaneous sort of reaction by just playing with sort of the concentrations. Any questions on any part of that there? All right, one more here. For the following, balance the redox reaction and calculate E and K for this reaction here. Okay, let's take a look. And in this case, our cathode is going to be this guy here. If you're not sure, you can actually probably just look at the chromium. That would be the easier move. You got a +2 and a +3, which means it is losing electrons. So this guy would be my oxidation, and by default, that would be my reduction. You could also look at the sulfur there. It's like a 2.5 on that side, and it's like a +2 on that side. So it goes down a little bit there in terms of reduction. So we can calculate E of the cell pretty easy by just taking our cathode minus our anode. So in this particular case, this guy being our cathode and that being our anode, we would take 0.17 minus a minus 0.5 volts. So we're basically going to add those guys together, and that gets us 0.17 plus a 0.5. Gets us a 0.67 volts in this case. Any questions up to there? Now that we have that, really, we could get to our equilibrium constant equation, which is our RTNF natural log of K, which does come from the Nernst equation to get there, as we just talked about. At this point, we have 0.67 volts equals our 8.314. Our temperature here, which would be 298. Our moles of electrons, we can see we do need to really kind of multiply this guy by 2, right, to get these guys to cancel out. So we should be going with 2 moles on this one. And our Faraday's constant, 96,500 joules per volt per mole. And natural log of K. So I'm going to clean up there on the left-hand side and then divide it over. So 8.314 times a 298 divided by a 2 and divided by a, not 2, a 96,500. Looks like it gets me basically 0.67 volts equals 0.012837 natural log of K. Obviously bringing this to the other side and dividing gives us 0.67 divided by that. Gets us a natural log of K is equal to 52.19. At this point, we're going to E both sides. And when we do that, we end up with a K value that is, we'll call it 4.6 times 10 to 22 in this case. Any questions on any of that there? Once again, these guys do agree with each other. 0.67 volts positive means the reaction should be heading towards the product side, right? In our spontaneous delta G, that means we should have more products than reactants, which means our equilibrium constant should be a large value, which it is here as well. So again, those guys do agree with each other. Any questions on any of that? To balance the equation, just got to flip it around. I think I missed that part there. Maybe I have it right here. I don't. But to balance the equation, we just simply flip this guy around, and that would get us basically like a 2 there and a 2 there, basically. And then a 2 there. Now we should be good. All right. Any questions on Nernst equation, calculating K, E of cell, galvanic cells? Okay, then we're going to talk a little bit about batteries here. You're really just sort of responsible for understanding kind of some of the similarities of batteries and galvanic cells and maybe some of the differences. A battery is a galvanic cell or a series of them sort of hooked together for direct current at a constant voltage. They are self-contained and obviously had no need for a salt bridge as you move around in your battery compartment. So let's take a look at some different types of batteries. This is sometimes referred to as a dry cell battery. And I'm going to go with Duracell perhaps here. This is an anode, which is the zinc container that's in contact with MnO2 as an electrolyte. The cathode there is our carbon rod that's in the middle. And basically, we have our redox reaction happening here. So we have our zinc anode where our electrons are going to basically go out through the wire and come on back through. That's again why when you open up a battery compartment, there is a wire in there, right? Where you kind of put your battery into. Again, that sort of functions as the wire that connects both parts of the salt bridge or both parts of the galvanic cell. We typically don't have a salt bridge, but a lot of batteries have what we like to call battery acid when it leaks all over the place. But that battery acid that's inside is usually a strong electrolyte, and that sort of functions like a salt bridge in a battery to help keep everything kind of going correctly. This is also why if we put our batteries in backwards, right, they don't work because you just made a non-spontaneous process. So you have the other way, then you have your spontaneous process occurring. All these type of batteries here will give you the same voltage, 1.5 volts, just different sizes, right? Have a capacity to go longer. We have AAA, AA, DC batteries, and never the size you need when you need a battery. But we have all the different ones, but they all basically will run at 1.5 volts. And we look at sort of our reactions here, our half reactions. This is again zinc going from 0 to +2. And then obviously our reduction happening there with the Mn on that side. And here's the overall reaction. You're not responsible, obviously, for the overall reactions or anything like that, unless I become really upset with your glass. I'm just kidding. Probably not going to happen. Another type of battery is a Mercury battery, and it's used a lot in medicine and electronic industries. It's more expensive than a dry cell. It also kind of functions a little bit similar. We have a stainless steel zinc anode that's in contact with mercury on the inside, and it contains a strongly alkaline electrolyte. Alkaline means basic, right? Yeah, so that is why we have some potassium hydroxide, which is a very strong electrolyte. Once again, sort of acting as like a salt bridge with inside there. There's no change in electrolyte composition. So when we look at the overall reaction, it involves pretty much only solid sort of substances. That is really a key when you look at the reactions for batteries of like long life, is like solids being formed there on the overall reaction. Also very helpful, as we'll see in a second, for like rechargeable type batteries, is having those guys sort of in that state. Get a little less voltage on this one, 1.35, but it has a higher capacity because of really not degrading all that kind of stuff. You're still left with a lot of the solids, which allows this reaction to sort of continue. Once again, our zinc going from 0 to +2 here, our mercury going from +2 to 0 in that case on the other side. Lead storage batteries, which are pretty much what's in our cars. There are basically 6 cells lined together, which is why in most cars that have a battery like that in their engine, traditional, I guess, is a 12-volt battery that you have there. So 6 of them each at like 2 volts each. Each of them is a lead anode and a cathode made of lead dioxide. And a lot of them are sealed these days. But we can recharge it, battery, by reversing the normal electrochemical process, by applying an electrical voltage to it. And sometimes we need to jump your battery. That's what you do, right? You kind of apply a little voltage, gives it a little jump, gets it going. Good health of a battery, you could check its density of it. And also sometimes you have trouble in very cold weather because all the inner liquid parts gets a little bit frozen sometimes and doesn't allow everything to flow as good as it should be. And obviously here's a cross section of a car battery. You should not cross section your car battery or open it or anything like that. But we have once again a very strong electrolyte solution there, acting to keep everything flowing. And then we have our cathode, which is our positive terminal, and our anode, which is our negative terminal there. And again, here we see our lead going from 0 to +2 being oxidized in this particular case. And our lead on the bottom there going, excuse me, from +2 there on that side, and +4 starting with being reduced in this particular case. Again, we have a lot of solid being formed in the overall reaction, which allows it to sort of regenerate and go on for a good period of time. Nowadays, batteries are a lot of times not even in the engine compartment, right? They're like in the trunk or underneath the back seat sometimes, but they will kind of pull the, if in case you need to jump yourself in the actual engine compartment. This is a lithium or solid state lithium battery. The anode here is a carbon sort of graphite material. It has holes that allows really the lithium to sort of migrate through it. And the cathode side is usually some type of transition metal, like cobalt there, that can hold the lithium ions as they travel through there. It can be recharged hundreds of times because it's sort of a solid state and we get solid. In addition, lithium is a very light metal, which is like wired cordless drills and stuff like that are lithium powered batteries, right? And stuff like that is very light. And it can be recharged a lot of times with not a lot of loss of sort of life as it's being recharged. This is a fuel cell, which is technically not a traditional battery, but it sort of can function very similar to a battery. This is a hydrogen fuel cell, which years ago, that's sort of what they wanted to make cars run on, basically, because the overall reaction there is basically water is what we're making. But to do this, you need kind of shoot in some oxygen, some hydrogen in there. And obviously, bless you, we have a very strong electrolyte solution to help keep everything running. And obviously, we could use this to power a motor like in a car. And again, the benefit here was that pretty much you would just be producing water. We obviously are not a hydrogen economy, right? And we don't have pumps of hydrogen around a lot to make that work. But what's happening here is, again, our hydrogen going from 0 here to +1 being oxidized. Oxygen going from 0 to -2 being reduced in that case. In this traditional cell, it would require obviously a constant input of oxygen, hydrogen in this particular case. Any question on batteries there? Let's talk a little bit about corrosion as well. Corrosion is pretty much an oxidation reaction that occurs for metals. So any metal that's kind of goes through a oxidation sort of reaction will basically be considered going through corrosion. A fifth of our steel is sort of made to replace iron that kind of goes bad. All metals that have an SRP value less positive than oxygen will pretty much go through corrosion. That's because when you have oxygen and you have a metal that is less positive SRP, which one would be the cathode in that case? It would be the oxygen would be the cathode because the metal is less positive, which means the metal would be the anode, which means our poor metal is going to go through oxidation basically, right? And that's going to cause corrosion basically of the metal. So any metal that again is less positive than oxygen is susceptible to going through corrosion. And it is going to be a spontaneous process in that case when that occurs. Most metals form a thin oxide that actually protects the inner metal from further corrosion. So not necessarily all corrosion is necessarily a bad thing. It can serve to protect sort of what's inside. And aluminum is an example of that. When it kind of goes through corrosion, it forms this nice layer that, you know, sort of protects more metal from going through actually corrosion. The problem though is iron that we use a lot when it does go through this process, you basically make rust. And if you have rust, you basically could just kind of wipe it off. The problem with that is it then exposes brand new metal that can continue to go through oxidation and fall off, and new metal going through. Before, pretty much, we probably all seen maybe a rusted piece of metal. You could almost just kind of push right through it, right? There's not much left there other than the corrosion and stuff like that. Sometimes corrosion is expensive. Copper forms a nice greenish patina color, right? That sometimes people really like. Gold, which has an SRP value of 1.5, that is larger than oxygen's SRP value, which means gold will not corrode, because in the case of gold and oxygen, it is the gold that will then become the cathode because it's more positive, and the oxygen would be the anode. Thus, no oxidation will occur on the piece of gold metal. Steel, as I mentioned before, is very susceptible to going through corrosion, and rust basically has a lot of non-uniform pockets on it, which can basically keep the moisture in there, right? And basically, you just need a little bit of iron, a little bit of oxygen, and some moisture, and you have rust that's going to basically form. So it actually happens in a couple of steps. The iron actually goes to iron 2 as the electrons flow through. And then the iron 2 actually will then get further sort of oxidized to iron 3 oxide, which basically is rust. And that's the process here. Again, kind of starts as iron 2, then gets further oxidized to iron 3. And again, these sort of pits that are metal that you can't really see are iron is a good place for water and moisture to kind of sit, for everything to kind of come together to form our rust, which then can just fall off, costing you lots of money, sad faces. You then have to replace it. Then you're happy till it falls off again. Then you're sad again. It's a whole vicious cycle to corrosion. Yes. But there are good news. You can prevent corrosion, right? And we can prevent corrosion by a few different ways. And just to end with a happy face there, we'll go back to a happy face here by preventing corrosion. One way is you could obviously apply some type of coating over it, like paint. They sell Rust-Oleum paint, right? So to prevent rusting. You could also do some type of plating. So chromium tin can be used. You could also do some galvanizing, which basically, since zinc is more active than iron, what happens is all the corrosion sort of occurs on the zinc rather than the iron. So when you sort of galvanize something, you can now look at the SRP values between iron and zinc. And we actually see that the iron is actually more positive in this case, which then it would be the cathode, while the zinc is more negative and it would be the anode, which means all the bad oxidation stuff would occur on the zinc. So it sort of acts as a sacrificial sort of coating for that. You could also do some alloying where you add some other sort of elements that sort of change the SRP value of a particular metal. Another common way is what is sometimes referred to as cathodic protection. And magnesium, for example, connected by a wire to an iron sort of pipeline or tank. Magnesium is a better reducing agent than iron. And that means if magnesium is a better reducing agent, it is going to go through oxidation in that case, which means all the bad, again, oxidation happens at the magnesium spot, keeps the iron tank from going through oxidation and leaking, probably since you buried it underground in a lot of cases. That's why I used to see gas stations, they would dig up after so many years, the parking lot there to fix these tanks. So here, if you had, again, a storage tank that was underneath, obviously there's a lot of moisture and stuff within the sand here. And with the magnesium here, the oxidation is going to all occur here at the magnesium and not on the iron tank, and thus should hopefully preserve it a little bit better. Any questions on corrosion? So you do need to know what corrosion is, some ways to protect yourself against corrosion. Any questions on that there? All right, we will lay it up there. We just got one more